Hi there. So here in section 4.2, we're going to look at two theorems that help us further analyze our graphs, and those will be Rolle's theorem here on the first page and the mean value theorem on the second page. So we'll go ahead and start right away into Rolle's theorem. And Rolle's theorem says that if we're going to let f be a continuous function on the closed interval from a to b and differentiable on the open interval from a to b. And so then it goes on to say that if f of a equals f of b, then there's at least one number c in that open interval such that my derivative at that particular c value is equal to 0. So now if you remember that whenever your derivative equals 0, that's going to be indicative in many cases of a maximum or a minimum point. And so if I have two points here on my graph, A and B, and they equal one another, right? F of A equals F of B. There's no way I can then draw a continuous graph, okay, and I not go up and have to come back down and hit the other point, or start here at A and go down, but then I have to come back up. Either way I draw my graph here, if it's going to be continuous and differentiable, I have to be able to get a maximum or a minimum. So I'm just going to draw it so that we've got a maximum. And so you can see here then that in this particular situation, f of a equals f of b, and I have a point up here, which we'll call that's our c value, and at that c, I've got a horizontal tangent line, and so remember, at that horizontal tangent line, what that means then is that my derivative is equal to 0. I've got a horizontal tangent line there. All right, so with that said, let's come on down and let's work a little bit closer here with Rolle's theorem. It says steps to verify Rolle's theorem. You have to always make sure that your function's continuous and differentiable. That's where you're going to be specifically most often just putting it in your calculator if you don't know what the graph itself looks like. And then from there, you're going to plug in the endpoints, find f of a and f of b, and make sure that they're equal to one another. And as long as those two first stipulations are met, then you continue on with Rolle's theorem. But if either one of those are not met, then we'll back out, okay? And we'll say that Rolle's theorem doesn't apply. In step 3, then we're going to find our derivative. We'll set our derivative equal to 0, and that will find all of our c values where we would either have a maximum or a minimum point, okay, in that particular given interval. So here in example 1, our function y equals, or f of x equals x to the 4th minus 2x squared, and we're just going to look at it over the interval from -2 to +2. So I'm going to kind of think about my stipulations here. Now I'm going to determine if my function is continuous and differentiable. Well, hopefully you recognize that this is a polynomial function, so it's got to be continuous. Differentiable, you remember, you just want to make sure that you don't have any asymptotes, you can't have any sharp turns in your graph, remember, or a vertical tangent line. You can't have any of those things in order to be differentiable. So if you were to pop this in your calculator, you would see that it looks somewhat like a W curve, and actually, I'll go ahead and get us a fair graph here that kind of looks, starting in here, it looks something like this. Rough sketch at the moment, and I'm just focusing on from -2 to +2. So we can tell then, yes, this graph is, and I'll just write here, it's a polynomial function. So we know then that it is continuous and differentiable. So we're good to go with stipulation 1. Step 2 said we need to determine that f of a equals f of b. So here's your a and your b. So I need to find f of -2. So that means go to your function. Everywhere you see an x, you're going to plug in -2. And we pop that in our calculator. If at any point during the video that you need to, stop the video so that you can put it in your calculator and verify it for yourself, I highly encourage you to do that. So, but if you do this math here, that should land you at a +8. Likewise, I'm going to plug in the upper endpoint. So everywhere I see an x, I'm going to plug in 2. So I have 2 to the 4th minus 2 times 2 squared. And if you put that in your calculator or evaluate it, you should also land at +8. And so now what we're finding here then is that, yes, f of a equals f of b. So f of, in our case here, f of -2 equals f of positive 2. So the two stipulations for Rolle's theorem has been verified, so we're good to go. We continue on then to find f prime of x. So f prime of x equals, taking our derivative, nice power rule here, so I would have then 4x cubed minus 4x. All right, so that was step 3. Step 4 says take that derivative and set it equal to 0. So I take 4x cubed minus 4x, set it equal to 0, and I solve for x. So in order to solve something like this, I'm going to factor out what these two terms here have in common. Hopefully you would agree. They both have a 4x in common. Write what I have left over, so that'd be x squared minus 1. Remember, the rule is from here that every factor that has a letter with it would get set equal to 0. So I would set 4x equal to 0 and x squared minus 1 equal to 0. And technically, you could take x squared minus 1 and factor it further if you wanted to go that route. Either way is fine. Over here, I solve for x, so you should get x equals still 0. Over here, we'll pull the 1 over, so x squared equals 1. Take the square root of both sides, so x equals plus and minus 1, because remember, anytime you take the square root, you get a positive and a negative. So we are saying then that all of the c values where we would have horizontal tangent lines where my derivative equals 0 happen at these 3 spots. And if you come back over here and look, okay, well, I can kind of verify some things. So we'd say here, here's my 8, so negative 2, 8, and positive 2, 8. And we can see that we have horizontal tangent lines here, here, and here, and they so happen to be happening at -1, 0, and +1. And they are indicative now of local max and min points. So we have max and min points where f prime of x was equal to 0, and that's x equal 0 plus or minus 1. So those are your 3 c values there, okay? All right, I'm going to scoot on down to example 2. In example 2, the absolute value function, so you should be able to say, yep, that's continuous. Differentiable, interval here is -4 to +4, so think about what this graph looks like. So if I put in -4, then I'm going to get -1, 2, 3, 4. It's going to be -2, absolute value of -2, +2. Let's put in 2, or let's put in -2. -2 is going to give me 0. And if I put in 0, I'm going to get 2. And I'll put in +4. Let's put in the other endpoint, +4. 4 plus 2 is 6. 2, 3, 4, 5, 6. There's my 6. All right, so there's my -4 to +4. And if you were to put this in your calculator, and hopefully you already have a good understanding of what an absolute value function would look like, it's always your hard V-shaped curve. Is this function differentiable in your interval? And hopefully you would agree that no, it is not, because right here at this vertex point, you would have a vertical tangent line. So therefore, we are not differentiable at x equals -2, which is part of my interval. Now, if I were just looking at the interval from 0 to 4, I'd keep going. But that's not my interval here. I'm looking at the interval from -4 to +4, and I have a place where I'm not differentiable. So Rolle's theorem does not apply. Theorem does not apply. And I'll just put in here for in parentheses, it's not differentiable at x equals -2. All right, we'll scoot on down to example 3. Example 3, this is just another polynomial function. It's just written out in factored form. So therefore, it is definitely going to be continuous and differentiable because it's a polynomial function. All right, so first step has been established, so then we need to make sure that f of -1 and f of 3 give us the same value. So f of -1 is equal to -1 minus 3 -1 plus 1 squared. All right, so we can see here in the second parentheses, I'm going to get 0, and 0 squared is still 0, but 0 times anything, 0. All right, let's do f of positive 3. I get 3 minus 3 times 3 plus 1 squared. It doesn't matter about that second parenthesis. The first parenthesis gives me 0. 0 times anything is 0. So we're seeing again here that f of a equals f of b. So Rolle's theorem applies. The polynomial is continuous, differentiable, and my endpoints are equal to one another. So my next step then is that I need to find f prime of x. All right, so I'm going to go through finding f prime of x. You've got a couple of options here. Again, this might be a problem that you want to stop from here and try this derivative on your own, try the rest of this problem on your own, and then come back and check yourself, or check yourself by the solution key that's posted online in Blackboard. All right, so f prime of x equals, I'm just going to choose to use the product and chain rule here to solve this, to find this derivative, but you could also FOIL this out and multiply it times x minus 3 and then just solely use power rule. Okay, so that's also another legal option to find your derivative. Either way is going to work you there, though, get you there. All right, so f prime of x. So here's my first and here's my second. Derivative of the first, so that derivative of that x is just 1, times the second, plus now the first, x minus 3, times the derivative of the second. So when I take the derivative of this second, then it's going to be 2, you can use the u substitution if you need to, but it'll be 2 times that entity, x plus 1 to 1 power less, times the derivative of what's inside, which is just a 1. All right, now from here, I'm going to, now I've just got to clean this up. So the first term, I've got x plus 1 squared, so remember that means x plus 1 times x plus 1. Back here, I'm going to have my x minus 3, and I'm going to take that 2 and distribute it through there, and that'll be 2x plus 2. You can take that 2 and distribute it to either parenthesis there that you want to, okay? But just don't do it to both, okay? And then, of course, times 1 is just still itself, all right? So in that first one, you're foiling. I'm going to x squared. I get outside and inside are both x's, so that'll be a plus 2x plus 1. Back here, I'm foiling. I got 2x squared. Outside's 2x. Inside's minus 6x, so that'll be a minus 4x minus 6. Combine like terms, and I have 3x squared minus 2x minus 5. Here's my f prime of x. All right. Now I want to set f prime of x equal to 0, so I'm going to set 3x squared minus 2x minus 5 equal to 0. Factor. The only way to multiply to give you 3x squared. The only way to multiply to give you 5. 5 and 1. Put my 5 in the front, 1 in the back. Outside is giving me 3x. Inside's giving me 5x. Your goal is that middle term, which is a negative 2x. You can get that, but you have to make your 5 negative. So minus plus, and then it checks at the end. Negative 5 times positive 1 will get me my negative 5. I would then set both of these pieces here equal to 0. So 3x minus 5 equal to 0, and x plus 1 equal to 0. They both are factors. They both have letters, so they both get set equal to 0. Solve for x. So x equals 5/3. Over here, solve for x. X equals negative 1. And I see one, so we are getting 2 answers here, and there's something I didn't stress earlier here in the video, so I'm going to go back and do that to make sure so that you understand why here I'm only going to be choosing the 5/3. And if you go back up and look, like I said, I didn't stress it, but I need to come back up here and look. We're finding step 4, you're finding where your derivative equals 0, and you're setting that derivative equal to 0, but it has to lie in the open interval. So make that notation here. It has to be in the open interval, meaning you can't include, get this smaller so it's easier to read. You can't include endpoints. Okay, because we would not have horizontal tangent lines at our particular endpoints. And if I were to graph this function for you, if you were to put it in your calculator, you would see that it looks, right, -1 and +3. So here's my -1, there's my +3. And we know from earlier that at -1 and +3, our function's equal to 0. At 5/3, we're getting so 5/3, 1 and 2/3, so we're getting a minimum point down there, and should be crossing the y-axis down here at -3. Graph looks something like this. Just, there we go. Kind of clean that up just a tad. Right, and there's our horizontal tangent line here happening at our 5/3, roughly in there, that C value. But it cannot occur at an endpoint, so that's why we exclude. And so I'll make that note here. We exclude because it's an endpoint. We will flip it on over and then discuss now the mean value theorem. With the mean value theorem, there's not a stipulation that f of a has to equal f of b, okay? So it says here for the mean value theorem, your function has to be continuous on the closed interval and differentiable on the open interval. And it's saying then that there exists a number c in that open interval such that your derivative at that c is equal to f of b minus f of a over b minus a. And let me just say this f of b minus f of a over b minus a, that's talking about the slope between these two endpoints. So it's saying then that the slope of the line between those two endpoints, that there exists a c such that the slope, the instantaneous rate of change, right? Let me see if I can find that point for us. It would have, the tangent line there would have the exact same slope, meaning these two lines, these purple lines here that I'm graphing, are parallel to one another, or as best as I can make it here, okay? So here we're saying that the slope of your tangent line, and this would be my c value, so there's my c value there. The derivative at c would have an instantaneous rate of change that would be equal to the average rate of change between the endpoints here, okay? So in other words, they're saying that our instantaneous rate of change at c is equal to the average rate of change between A and B. Or the average rate of change in that closed interval from A to B. And we're specifically looking at these two endpoints. I'm saying that the slope of the line passing through the endpoints is equal to the slope of the line passing through that tangent line there, okay? All right, so let's add a little bit more to this graph and try to make this connection here. If this ordered pair has an x value of a, then its y value would be f of a. And likewise here for my b, its x value is b, and then its y value would be f of b. So this formula that you see up here, this f of b minus f of a over b minus a, that is nothing more than that's your slope, right? Slope is y2 minus y1, so think of this as f of b minus f of a over b minus a, right? Here's your first order pair and your second order pair. So think of this as like my x1, y1, x2, y2, and we know slope as y2 minus y1 over x2 minus x1. That's all that is. That's the slope between those 2 points right there. And we're saying then, hey, I can find a horizontal tangent line. I can find a point here on that graph where I would have the exact same slope as the slope between those 2 points, okay? All right, couple of things then. How do we verify mean value theorem? Your function still has to be continuous and differentiable. Remember, you're continuous on the closed interval, differentiable on the open interval. You're going to evaluate your endpoints into f of x. Essentially, you're finding f of a and f of b. Really the only stipulation on this problem is that you have to be continuous and differentiable. If you're not continuous and differentiable, you stop, okay? But as long as you're that, then you continue on, and we're going to be able to find what we need to. We're going to be able to find all of the c's where our derivative is equal to the slope between the two endpoints. So as long as you're continuous and differentiable, then you're going to keep going. You're going to evaluate your endpoints. They do not need to be equal for the mean value theorem, as you can see here from the picture itself. F of a and f of b are definitely not equal to one another. You're going to calculate the slope between the two endpoints, okay, using the classic slope formula. Then you're going to find the derivative of your function and set your derivative equal to your slope and solve for x. X has to be in the open interval, okay? I'll try to remember to do that here. It has to be in that open interval. Okay? All right, so let's come on down and let's look at these 3 examples. So in example 4, determine if the mean value theorem applies, and you can see my abbreviation, MVT. Use it for your liking as well. If so, if it applies, meaning if it's continuous and differentiable, then we're going to find all the c in our interval such that the derivative is equal to the slope between the endpoints. If not, explain why the mean value theorem does not apply. All right, so first things first here in example 4, I would graph this, and let's make sure that it's continuous and differentiable. So if I take a look at, maybe I'll just come over here and do my graph. I'm interested from 2 to 6, 2, 3, 4, 5, 6. So 2 to 6. If I plug in 2, hopefully you agree, you're going to get 0. And then if I plug in 6, 6 minus 2 is 4. Square root of 4 is 2. Hopefully you're also, and you can use your calculator as well, but hopefully you remember what square root functions look like. Roughly something like that. Okay. I won't put an arrow there because we know we've got a finite. We are just looking at it from 2 to 6. Okay. But hopefully you can agree here then we are continuous and differentiable. All right, so what that means then is that we're going to be able to find a point on this interval where it has the exact same slope as that line that I just drew. Okay, that the slope between these two endpoints here is going to be the exact same. We'll be able to find a point on that interval that will be the exact same as that red line there. Okay. All right, so step 2 says evaluate my endpoints. So I'm going to find f of a and f of b. So I'm going to find f of 2, which we actually already did. Square root of 2 minus 2, square root of 0, which is 0. F of 6, square root of 6 minus 2, square root of 4, which is 2. All right, so let's, we actually did create ordered pairs here. Let's go ahead and write these ordered pairs. We put in an x value of 2, got out a y value of 0. We put in an x value of 6, got out a y value of 2. All right, now let's find the slope between those 2 points. That's going to be the slope of this red line here. So m equals, I'm going to think of this as my first order pair, so this is x1, y1. This is my second order pair, x2, y2. So slope is y2 minus y1, so 2 minus 0, over x2 minus x1, 6 minus 2. That gives me 2 over 4, which reduces to 1/2, okay? So we're now saying that the slope of that line over here is 1/2, okay? And then I need to next find the derivative, step 4, f prime of x. All right, so I'm going to take a moment and let me rewrite f of x. F of x equals x minus 2. It's the square root, so that's the same as raising it to the 1/2 power. All right, so now if I'm ready to find my derivative, you can use this u substitution if you like, but you might want to, for smaller functions like that, you might want to start thinking about it in this context. You can use power rule here. 1/2 times this entity, x minus 2 to 1 power less, so I'm subtracting 1, so that would give me a negative 1/2, times the derivative of that entity, of derivative of what's inside, which is just 1. All right, so then I'm just going to clean this up. I'm going to kick that x minus 2 to the negative 1/2 to the denominator. So I have 1 over 2, and I'm going to go ahead and write it as the square root, x minus 2. All right. Last step, you're going to set that derivative equal to the slope that you found. So I'm going to set 1 over 2 square root x minus 2 equal to 1/2. Problem like this, you just cross multiply. So I'm going to say 2 times the square root x minus 2 times 1. So that's going to give me 2 square root x minus 2 equals, over here, 2 times 1. Solve for x. So I'm going to divide both sides by 2. Square root of x minus 2 equals 1. Square both sides. X minus 2, when you square a square root, you just get what's inside. So x minus 2 equals 1 squared, still 1. Add that 2 over, so x equals 3. So if I pop over here, and there's my 3, we're saying then that the slope of the tangent line, let me get a different color, passing through that point would have the exact same slope as that red line, and hopefully you can agree here. That's pretty good for parallel in terms of drawing it freehand here on my graph on in your notes. So x equals 3 is that one spot where that happens, and you can clearly tell that obviously that 3 is in our interval because we're only looking at from 2 to 6. Okay. All right, let's come on down. If you feel, if you feel pretty good about that one, I would recommend pause the video, try example 5 on your own, okay? And then you can come back here to the video and check yourself, or check yourself by the solution key posted online. All right, so in this next one, f of x equals x squared, hopefully you agree. That's your parabola facing upward. That is definitely continuous and differentiable. So let me fix my pen. It's definitely continuous and differentiable. So I'm good to go there. All right, so now I evaluate my endpoints. And actually, even before I do that, maybe I should come over here and get us our graph so we don't get too lost once we get moving forward. So we are only looking at it from 0 to 2. So if I plug in 0, 0 squared, 0, I'll go ahead and do 1 and 2. So 1 squared, of course, is 1, and 2 squared will give me 4. And so we know that that's a parabola. Looking at there. Not exactly perfect, but not too bad. We knew it needed to have a curve in it. All right. All right, so let's evaluate f of 0. So 0 squared, that's still 0. So we just plugged in 0 and got out 0. Evaluate f of 2. 2 squared, which is 4. We just plugged in 2 and got out 4. All right. Now from there, let's find the slope between these 2 points. So m equals, I'm going to think of this as my first order pair, my second order pair, so it'll be 4 minus 0 over 2 minus 0. 4 divided by 2, which is 2. There's my slope. All right, so this is a much easier derivative this time. F prime of x, just 2x. Last step, we set that derivative equal to our slope, solve for x. So one stepper there, x equals positive 1. All right, so box that in. That should be the only value then where the derivative for the slope of the line passing through these 2 endpoints would be equivalent to the slope of the line passing through that point tangent. Again, not too bad in terms of being able to show that those 2 lines there are parallel. All right. Lastly, I'll come down to example 6. In example 6, here's our function, x to the 2/3. And our interval is from -1 to 5. So look at that graph. If I plug in -1, I'm going to get a positive 1. If I plug in 0, I get 0. And if I plug in 5, I get 2, I believe. 2.9, it's almost 3. Okay, 1, 2, 3, 4, 5. There we go. All right, but if you were to plot this in your calculator, you would see that it's not smooth, that you have a sharp turn there at 0. So because I have a sharp turn, what's the problem? What am I not? Hopefully you agree you're not differentiable, right? You're definitely continuous, right? I'm definitely continuous. Check. But differentiable is a no. We are not, what am I, we are not differentiable at x equals 0. So we don't need to go any further. Mean value theorem does not apply. All right, that finishes up these notes. Thanks a lot. Bye.